So question 5 is a uniform motion question mixed with differential equations a bit. So basically we have a ball, it's thrown upwards from the edge of a building and it's 24.5 meters high. It can be nice to just like draw a diagram to kind of see what's going on. Here's our building. It's 24.5 meters high and we're throwing a ball. It reaches maximum height 2 seconds after it's thrown. So you can see it's thrown like that and it reaches here after 2 seconds. Model that neglects the effects of air resistance, calculate the time when it's thrown to when it lands at the ground. Okay, well, because we don't have to worry about air resistance, we can use the Suvat equations since our acceleration will be constant. So let's have a look at our Suvat, and we're going to look at from the start of the motion up until the top point, because we know information about the top point, and of course we want to make use of that information, which is why we're going to do it. Our S is going to be question mark. We don't know what that is. We don't know how high it goes. We don't know the speed it starts at. We know that when it gets to its highest point, the velocity will be 0. The acceleration is going to be minus g because it's pointing downwards, and time is going to be 2. So here we have an option. We could either find u or we could find s. Now, finding u isn't going to be very helpful because if we knew u, well then we could figure out how long it takes to get up to the top. But the thing is, we don't know how high it went up, so we can't actually figure out the total time it took. Because, well, I guess you could. You could throw it up, and then you could... Okay, you can do it both ways. I'll do it both ways just to demonstrate. So we'll do method 1 is just find u, and it'll be cool if we get the same answer. So then we'd have u, v, a, and t. Best equation for that, u, v equals u plus at. So we'll get 0 equals u minus gt, or minus g times 2, because time is 2. That means that our initial velocity is going to be 2g. And I'd just leave it as that because it's kind of easier to work with. We're trying to calculate the time when it's thrown to when it lands at the ground at the bottom of the building. So now we want to find from thrown to bottom. So the whole thing now that we know the initial velocity. So our displacement, sorry, I'll write them all out. SUVAT equals, whoops, that's not meant to be congruent, equals. So basically, we know that our displacement is going to be minus 24.5 because it's going to start here and it's going to finish 24.5 below. So we'll have minus 24.5. Initial velocity is 2g, positive 2g, it's going upwards. We don't know anything about v. Acceleration is negative g, and t is what we're looking for. You can see we have 3 things, and we can find t. U, a, t, and s. We can do that s equals u plus v over, no, not t, v. We have s, u, a, t. Oh, that's, of course, s equals ut plus at squared over 2, or half at squared. It's just easier to write like this. Minus 24.5 equals, oh, we're going to have a quadratic equation, 2gt minus gt squared over 2. We can multiply by 2 across. We'll get minus 49 equals 4gt minus gt squared. Rearrange it, bring it all to the left side. We'll get the gt squared minus 4gt minus 49 equals 0. We can use the quadratic formula for this, or there might be a nice way to solve it. I think there actually might be if we divide by g. Yeah, so if we divide by g, we actually get t squared minus 4t minus 5 equals 0. Factors of 5, we can have minus 5 plus 1, and that'll work. So we'll have t minus 5, and then t plus 1. That looks like a plus. A t plus 1, and this works because, of course, minus 5 times 1 is minus 5, minus 5 plus 1 is minus 4, so it works out. Therefore, t is either equal to 5 or t is minus 1. We can't have a negative time, therefore t is 5 seconds it takes to get to the bottom of the building. And now we can try it with the other method and see if we'd get the same answer. So I'm just going to copy this down again so we can have a look at it. So this time that we can just find s, okay? So we'll have s, v, a, and t. That'll be v squared equals u squared. No, we don't have u. We could use, is there even an equation that does that? So there's actually no easy way, unless you're like combining equations together and stuff. You can try it out for yourself, finding s, but I'm not going to do it just because it'll take too long, because I realize that you'll have to take 2 Suvat equations and kind of combine them together, but you can give it a go if you want. In part 2, we're given a more sophisticated model that does take into account the air resistance, which is minus kv, and we have this differential equation. K is a constant. Take the initial upward velocity of the ball to be 20 meters per second. Solve the differential equation. Okay, so we can take the minus g minus kv, we can divide by that to get it to the left side and bring the dt up. It's probably the easiest way to do it. And we'll have dv divided by minus g minus kv equals just dt. When you do that, then we can just integrate both sides. So velocity starts at 20, sorry, and it goes up to some velocity v. You can do it with not do the limits and just do plus c at the end and solve for that, but I prefer to do it this way. Time starts from 0 and goes up to t. For this integral, we do have to do a u substitution, or you can do it in your head, but I will do the u substitution just to kind of make it more clear. So we have the integral of 1 over minus g minus kv with respect to v. So of course, we can't integrate 1 over minus g minus kv, so we'll set our u equal to that. So we'll have u equals minus g minus kv. So that we'll have du over dv equals, that's constant, that's gone. We'll just have minus k. Or in other words, if we solve for dv, we can get that dv equals du over minus k. So we can replace our dv with du over minus k. So this will be the same as the integral of 1 over, and that's just our u at the bottom, that whole denominator, times du over minus k. Now, since k is a constant, we can't take it outside of the integral, just to make things a little bit easier, I suppose. We'll get minus 1 over k times the integral of 1 over u du. The integral of 1 over u du is just the natural log of u, so we'll have ln of u. Sorry, we have the minus 1 over k. So what we'll actually have is we'll have minus ln of u over k, because we have the minus 1 over k, plus c technically, but we won't be worrying about that because we have the limits. Then finally, u is just minus g minus kv, so we'll have minus ln minus g minus kv all over k. So that's what our integral will be when we do that. So what we'll get here is we'll get minus ln of minus g minus kv all over k. Technically we'll have a plus, we would have a plus c, but we have the limit, so we don't have to worry about the plus c because it'll cancel. So starting from 20 and going up to v equals, the integral of dt is just t, and from t to 0, well, you just have t minus 0, which is just t. Now we can just plug in the numbers. I might actually bring, no, it's okay actually. So what we'll have is we'll have minus ln of minus g minus kv all over k, plus, because we'll have minus the second bound, the minus and the minus here make a plus. We'll have plus ln of we'll have minus g minus 20k, because we're replacing that v with 20, all over k. That's equal to t. We can multiply both sides by k, and we'll get that. I'm just going to bring this one before the other one because it's the minus will be easier to deal with, I suppose. And we'll have ln of minus g minus 20k, and we'll have minus ln of minus g minus kv equals kt. I know there's a problem with the minus things in the ln, but you'll see it will work out, because when we combine these, we'll get minus g minus 20k all over minus g minus kv, which is equal to kt. You could multiply the top and bottom of this by a negative, and the top, because you can multiply the top and bottom of a fraction by the same thing, and we'll actually just get rid of all the minuses and they'll all turn into a plus if we multiply by a negative. E to the power on both sides, we'll get g plus 20k all over g plus kv equals e to the power of kt. We're not told what k is, are we? Yeah, no, expression for v in terms of t and k. So we'll have g plus 20k. I'm just going to do a few things. I'm going to move the g plus kv up there and move the e to the kt down there. We'll have over e to the kt equals g plus kv. Finally, we can bring the g to the other side, and we'll get that kv equals g plus 20k over e to the kt minus g. Finally, divide by k on both sides, and what we get, I guess you could combine these if you want into the one fraction, but you don't necessarily have to. Look at that, v equals, we'll have g plus 20k over, I'll write ke to the kt, oops, ke to the kt minus g over k. And that's one way we can write it. It doesn't really matter. As long as it simplifies out to that, it's okay. In the next part, we're told that k is this number, calculated the time it takes the ball to reach the maximum height. So when it reaches its maximum height, now it starts going upwards, doesn't it? Yeah, so it starts the upward velocity 20, and then it's going to be decreasing. So the velocity is decreasing because these are both always going to be negative. Because velocity is positive, and then this is obviously a negative constant. So we're basically going to be going upwards. So we can set v equals 0 at the maximum height, at max height. And so we'll have, and replace the k with this number, and what we'll get is 0 equals g plus 20 times 0.1225 all over, I'm just going to write k for now. I'm not bothered to actually go through all this. So I'll just write k for now, but I'll sub it in at the end because it'll be easier. K e to the kt, instead of writing out that big number every time, minus g over k. And we just need to solve for t. So we can multiply, what's the best way to do this? Okay, I guess we can bring this to the other side. We can get the g over k, or I guess we can bring them all up to the top. Actually, we can multiply by k. These two k's will I'll do it the other way. I'll bring the g over k to the other side, equals g plus 20k over k e to the kt. We can multiply both sides by k, and these will cancel out. And what we'll get then is that, and I'll bring the e to the kt up to the other side, we'll get that g e to the kt equals g plus 20k. Divide both sides by g, e to the kt is just equal to g plus 20k all over g. And then finally, take ln on both sides. We'll get that kt is equal to the ln of g plus 20k over g. And then divide both sides by kt equals 1 over k times ln of g plus 20k over g. Something I just realized, you didn't even have to do that. You could have gone from here and just subbed in your value for k, and that would have worked out just as well. But I did all that, so, but you can literally just do that. When you put that into the calculator, you get the t with the value of k that they give. The t is about 1.821, and usually we just do 2 decimal places. We can say 1.82 seconds. That looks like a 5 seconds. Finally, we're asked to write a differential equation for the rate of change of velocity of the ball on the downward part of the journey. So basically, let's just have a look at the ball and the forces on it, because obviously that's how you do differential equations. We can use F equals ma. So we'll have the weight pulling it down. We'll have mg. And I'm not sure, did they say the drag force was in the kV, or did they say that includes the effective air resistance? They didn't say that necessarily. But we can assume that the drag force is kV or mkV because they have it here. So yeah, we'll say mkV because they should cancel out eventually. Again, because here we don't have any m's. They must have all canceled out. So we can say mkV, and that's going to be going up because remember, drag always opposes velocity. So we'll have mkV going up, and then our overall acceleration will be going down. So what we'll have is that our acceleration, which is ma, will be given by, and then we can say going down is minus mg plus mkv. Divide everything by m, and a is just dv on dt, equals kv, again just rearranging, minus g. And that is a differential equation representing the velocity while it's going down. So you can see the air resistance has turned positive because the air resistance will be acting up, whereas here the air resistance was acting down since the ball was moving upwards. So yeah, dv on dt is kv minus g.